Alrighty, so this is your class summary for October 7th, Wednesday. Right, so a reminder that your quarter ends on October 16th, and not only is it the end of quarter one, but it is also the end of semester one for periods 1, 3, and 5. So these grades will go on your transcripts. And a reminder that if you have any makeup assignments to make up, or missing assignments, or things you want to redo, or quizzes you want to retake, please do so, especially if you have below a C minus. I will be making phone calls on Friday, October 9th, if you are currently not passing my class, and I will send you an email with 3 things to prioritize to make up, right? And also a reminder that if you don't know how to figure out your grade and stuff like that, if you go onto your Schoology page, all the details on how to figure out your grade, make up assignments, is listed here, right, on the right-hand side. So if you click on this, make up missing assignments and retake for medical chemistry, right, that should help you out in terms of figuring out your makeup assignments. Excuse me. All right. So for today, on Wednesday, we talked about how we use Half-Life, or something called Half-Life, to dose how much radioactive medication we need to give to patients, right? And how do we calculate that? So when we talked about this, we first watched a video about iodine 131. So I'm going to actually mute this and I'm going to click through the slides. So iodine 131 is often used to treat thyroid cancer. So this is the cancer of the thyroid gland. It's kind of where your throat is. And if you have thyroid cancer, you'll notice like a swelling in the throat and kind of like your upper jawline area, right? And oftentimes, if you have thyroid cancer, they'll give you a liquid or pill form of iodine 131. And that pill or that liquid form contains radiation, right? So what happens when you consume that radiation is that radiation goes inside your body. It's actually an unstable isotope, right? And it releases radioactive particles, right? So therefore, if you consume radioactive isotopes, you have to be in isolation or stay at the hospital away from people for a certain number of time, right? And at the hospital, they'll let you know how long to stay in isolation for based off of how much radioactive particles they give you in your treatment for that day, right? So our job as a medical chemist is to calculate how long do they need to stay in isolation or in the hospital, right? But in order to understand that, we need to talk about something called half-life first. So here, let's model what half-life is. All right, so in this simulation, I'm going to click reset. And you'll notice that I have a bucket of polonium. So polonium is another unstable or radioactive isotope. Right, so if I start with 10 poloniums, notice that they were shaking because they're unstable. And when they're unstable, boop, they're going to start shooting out radioactive particles. And notice that when they shoot out radioactive particles, they start to change, right? So we started out with the yellow version, polonium 211. And then after they shot out their radiation or radioactive particle, it turned into what we call the daughter isotope, or lead-207, right? So this is the process of what's happening inside a patient's body when we give them a radioactive particle to consume. But what is this thing called half-life though? So to do that, I'm going to add 100 poloniums at a time. So 1, 10, 20, oops, let me pause this first. 30, 40, 50, 60, 70, 80, 90, 100. So I have 100 polonium. I hit play. All right. So notice what's happening. The polonium that's yellow is releasing its radiation, releasing its radiation, releasing its radiation. And I'm going to press the pause button once it hits this half-life time. There we go. Okay, so I stopped and hit pause once it hit the half-life time. And I mentioned earlier that we started out with 100 of these yellow poloniums, shown here and here. And at the half-life time, oh, look at that. It's at 52. So that's about half, right? So half-life is just the time for the total amounts of radioactive or unstable isotopes that you have to decrease by half, right? So using this knowledge, we can figure out how much radioactive isotopes are in our patient's body if we know the radioactive isotope's half-life, right? So let's talk about this particular radioactive isotope. Right, so I want you to notice a couple of things. Here, I'm starting out with 10 grams, or this many, of radioactive cobalt-60, right? A different one. So if I start out with 10 grams here, after the first half-life time, it will go down by about half. So notice here that if it's 10, well, what's half of 10? It's 5, right? So that's how you get 5. So that's after one half-life time, right? So my half-life time for each isotope is different. So for cobalt-60, it's going to be 5.27 years. So if I wait 5.27 years, this 10 grams will go down by half. Right, so I will only have 5 grams of cobalt-60 left. Well, what happened to the other half? Well, the other half did not disappear. It just turned into the daughter isotope. Right. So on here, if you notice that here I started with 10 grams of this amount, waited 5.27 years, I have half of that, and the other half that's gray just turned into the daughter isotope, right? Meaning that the ones that are now gray used to be red, but they gave off their radiation here, right? And now it's become this. Well, now that I have 5 grams left, what's going to happen when I wait another 5.27 years? Well, it's going to go down by half again, right? And if I wait another 5.27 years, it's also going to keep going down by about half. Right? So half-life is just the time it takes for the total amounts of our radioactive isotopes in a dose to go down by half. Right? So for all the problems you're going to do in your Nearpod, you're literally just dividing by 2 over and over again. Okay, so at this point, I released the class to do their lesson 3.10 on Nearpod in order to learn the details of how to calculate half-life, right? So all the practice problems that I show you are actually on Nearpod. So at this point, go ahead and go back to your Schoology page. Right? If this is still on here, I'm going to click on Homework, Topic 3. Atoms versus Cancer. Step 1, complete lesson 3.10 half-life and follow the instructions on the document. So if I click on this document, this is the title of my notes. These are the key ideas I need to take down in my notes. If I don't know how to set up my notebook, I linked this here, but you should have done it at the start of the quarter. Then you're going to go to your Nearpod lesson. And then it's going to ask you for a code. So notice that the code is linked here. All right, so from here, you can start the lesson. All the instructions are in blue. Right, and then there's a video of me explaining all these concepts, and then all the slides after this were from the video, right? Just in case I went too fast in the video, but always feel free to pause in the video as well. All right, and then finally, the end of the slides is just a check-in to make sure that you fully understand what's going on. All right, so that's the first lesson. The second part is to make a copy of this document. So this is your main homework. Notice that it says to only complete at least 2 sections. So this is one section, basic. Basic is, this should be straight from your notes, right? And then proficient are practice problems that I did in the Nearpod lesson. Right. So if you complete basic and proficient, that counts as completing all of your homework. If you're like, oh, Half-Life is super simple, I totally understand this, feel free to challenge yourself by completing the proficient and advanced section instead. Right. Once you're done with this, go ahead and upload this onto Schoology. If you don't know how to upload this onto Schoology, you can watch this video from Mr. Ta that teaches you how to do that. All right. So that's pretty much it for our Wednesday, October 7th lesson. If you're still kind of stuck or confused, always feel free to email me at qquan@slusd.us, or you can direct message me on our Instagram page at Quan Medchem.